Hi, chemistry. Last class we talked about writing a code that can describe where an electron exists. Today we're going to talk about how to make that code more functional. So just to recap, last class we talked about how a code can describe where an electron exists, and that code would contain 4 different quantum numbers. And those quantum numbers are N, L, M sub L, and M sub S. And those 4 quantum numbers describe the size, the shape, and the orientation of the orbital where the electron exists. M sub S is going to describe the spin of one electron. And so that orbital, remember, is a 3-dimensional space described by shape, size, and orientation where the electron can exist. And each orbital can hold 2 electrons. And that's why we need the spin number, because the spin number is going to tell us which of the 2 electrons inside that orbital we're describing. So for example, if I have an electron and it exists in the first energy level, oops, that should be M sub L. Okay, if I have an electron and exists in the first energy level, that first energy level is the only shape in there is a sphere. So I'm in the first energy level. That's what the N tells me. My shape is an S. So L's can be 0, 1, 2, or 3. A 0 is going to be an S. A 1 is going to be a P. A 2 is going to be a D. And a 3 is going to be an F. So my L value would be 0. Now, M sub L is orientation, but remember, spheres can only have one orientation. Its M sub L value can only be a 0. There's only one value for it. So M sub L has to be a 0. And then M sub S we can pick. So one of the electrons would have a positive 1/2. The other electron would have the exact same quantum numbers, but would be a negative 1/2. So here I have the description in terms of quantum numbers for both electrons inside that 1s energy level. Let me give you another example. We'll do an electron that exists inside the 2px orbital. We can do both electrons that exist inside the 2px orbital. So this would be a good time to pause the video and see if you can predict the quantum numbers for an electron that exists inside the 2p orbital. Okay, so the N is going to be 2, since it's a 2p orbital, it's in the second energy level. The L would be a 1, since it's the dumbbell shape and not the S shape. Remember, our codes for the possible L's are on this side. Now, orientation, remember there's 3 different possible ways the p orbital can be oriented. 3 different possible ways, because the M sub L values can be 0, -1, 0, and +1. And so for an X, you can just pick one. It's not like a -1 is always an X, a 0 is always a Y. They're kind of just used to say like, okay, 3 different ways to orient it. So let's just say a -1 for now, and then you have to choose a spin, +1/2. That would describe one of the electrons inside that orbital. If you want to describe the other electron inside that same orbital, you would use the exact same quantum numbers to describe the orbital again, and then just give it a negative 1/2 to mean it's the other electron that's spinning the opposite way. Okay, so these are quantum numbers. Now in AP chemistry, what I would do is I would ask you a question like I just asked you. Give me all the quantum numbers to describe an electron that lives inside this specific orbital. That would make a good test question for AP chemistry. Or I could give you a set of quantum numbers and say, is this valid? Is this describing a real electron that actually exists or not? That would be another good test question for AP chemistry. Now, quantum numbers can be a lot to remember. It's a lot of system to memorize. And so in chemistry, we actually don't hold you accountable for the quantum numbers. So what we do instead is we deal with a code that still represents the quantum numbers, still represents where electrons are inside the quantum mechanical model, but the code is a little bit simpler. It's a little bit more pared down. And so that's what I want to introduce you to today. I want to introduce you to that simpler code that tells us where electrons live around the atom. And that code is called an electron configuration. Okay, now you may be saying to yourself at this point in time, hold up, Martins. If I didn't need to know this, why did you just walk me through it, girl? Right? So I walked you through it because I really want you to have a whole picture. I don't just want to give you electron configurations and be like, memorize this, right? I'm not going to tell you where it comes from, but I still want you to know it and be able to explain it and be able to do it. That's really hard to do. So hopefully by talking you through the quantum mechanical model and quantum numbers, you have this picture in your mind of like what it is and where it came from. And now what we can do is we can talk about electron configurations, and you will be able to make the connections without having to do the whole quantum number shebang on your own. Okay, so I tend to give too much information rather than giving you too little. That's the side I err on as an educator. If you want to just know what you have to know and memorize it, and you don't want to understand why, I get it. It's a little bit simpler, right? But this way, you will have seen the information once, you will have experienced it once, you'll have some semblance and reason of where it came from, and you can, when you encounter it in the future, it'll ring a bell. You'll be like, oh yeah, I talked about that once before. I know this, I can do this. So hopefully it kind of sets you up for success now and in the future. So you're welcome. Okay, let's talk about electron configurations. Okay, so let me walk you through a simple electron configuration to kind of show you what I mean. So again, we're trying to describe where electrons exist. We're trying to describe the electronic structure of an atom. So let's look at hydrogen and helium, for example. So we can draw the Bohr model for hydrogen. We know how many electrons it has by looking at the periodic table. Hydrogen has 1 electron, and according to the Bohr model, the first energy level can hold 2 electrons, and then the second energy level can hold 8 electrons, right? So hydrogen has 1 electron, it only needs 1 energy level. And there we are. That's the Bohr model. So an electron configuration is going to be a simplified version of the quantum numbers that tells us where those electrons exist. So the electrons exist in the first energy level. So I'm going to start with a 1. And that first energy level only has 1 shape. And that 1 shape is L equals 0, which is a sphere. And we represent that by the letter S. And then the last thing you have to indicate on electron configurations is how many electrons there are. So hydrogen has 1 electron. I'm going to put a little 1 superscript there. So that is that the quantum numbers simplified into a little code. Notice that my N is represented, my L is represented. The orbitals, or the orientation in the spin, are not represented. So again, that N is going to be energy level, or the size, how big that orbital is going to be. L is going to be the shape of that orbital. And then we have to indicate one other thing in the electron configuration, and that's the number of electrons that are in that orbital. Now notice, because we don't represent that M sub L, that orientation quantum number, all the orientations for one shape are going to get smushed together. So S's can hold 2 electrons. The P's, remember we have PX, PY, and PZ. They're just going to get represented by P. And so all the electrons, the 2, 2, and 2 that can exist, all get smushed into this one nondescript P. And so it actually just gets a 6. Same thing happens with the D. Remember, we have 5 different Ds that we can represent, all having a different orientation: XY, YZ, XZ. And then we have 2 on diagonals. All of those, each of those can all hold 2 electrons, but they all get smushed together for an electron configuration, so that D can hold how many? 10. Same thing happens with the F's. There's 7 different F orientations that can occur. They all get smushed together and we get an F14. So S's can hold up to 2. Notice they don't always. For hydrogen, if it doesn't have 2 electrons, you don't put a 2 in there automatically. You have to put the amount that actually exists. So S's can hold up to 2. P's can hold up to 6. D's can hold up to 10. F's can hold up to 14. Again, they don't have to. Okay, so let's draw the electron configuration for helium. So helium is going to be same idea. From the periodic table, we can look to see how many electrons there are. There are 2 electrons for helium, and they both exist in that first energy level. So the electron configuration for helium is going to be a 1s, and then there's 2 in there, 2 electrons in there instead of just 1 for hydrogen. So that's what a basic electron configuration is. Now here's the issue. Let me erase what I have and show you lithium. Okay, so lithium, we can look at the periodic table, figure out how many protons, neutrons, and electrons there are. We know lithium from looking at the periodic table has 3 electrons. The Bohr model for lithium would show 2 on the inside and 1 on the outside. But here's the rub. Where do we put that second electron? Or that third electron? The first 2 for lithium, I know they're in the first energy level, which is an S, and I put a 2 in there. The third electron for lithium is going to be in the second energy level. But what shape is it? And here's the deal. In order to be able to continue writing electron configurations, we have to know what order the orbitals get filled. So that's what I want to talk to you about next. It's called the order of filling. And orbitals are going to fill from lowest energy to highest energy. That's the order that orbitals fill. So in order to be able to write the electron configuration, you have to know what the lowest orbital energy is and what the highest energy orbital is and what the order is in between there. Now, there's 2 ways to know the order of filling of the orbitals, or the energy, the ranked for all the orbitals. I'm going to show you the simpler one first. Okay, so the simpler one is called the Aufbau diagram. Because what I'm describing to you right now is one of the 3 rules for writing electron configurations, and it's called the Aufbau principle. The Aufbau principle is that electrons are going to fill from lowest energy. Electrons fill from lowest energy orbital to highest. That's what the Aufbau principle is. And so what I'm going to show you is called the Aufbau diagram, which helps you remember that order of filling. So what you do is you just write out each of the energy levels separately with the shapes that occur inside them. So the first energy level just has 1 shape. The second energy level has 2 shapes. The third has 3. The fourth has 4. And then after that, we only have 4 shapes. We run out of shapes. They all just have 4. Okay, and so in order to know, you have to draw diagonal lines. 1s gets filled first. 2s gets filled next. 2p. 3s. 3p. Okay, so far, so good. So far, they've just filled in numerical and then letter order SPD so far, right? We filled all the 1s, we filled all the 2s, now we're filling the 3s, but here comes the problem. What fills next? According to the Aufbau diagram, where is our slashy line going to go next? It's not 3D, right? It's 4s. So 4s fills before 3D. Now, why does this happen? That's an excellent question. Remember, we're trying to describe what we see. We're not trying to make up the pattern ourselves. And so what we observe when we look at electrons going in and out of these energy levels is we observe that 3D fills after 4s. And so we're assuming it's just a matter of interference. Remember, the more waves that interfered, the more complicated the pattern became, right? We saw that on the salt on the speaker video. Same thing happens with electrons. The more electrons you shove into an area, the more complicated the pattern is going to be. So when you get enough electrons to actually fill that 4s and or 3D orbital, you have like 18 electrons already. You're trying to put in a 19th electron. It's a lot of electrons interfering with each other constructively and destructively, and the patterns start to get really complicated, and that 4D orbital gets bumped. It gets bumped to a higher energy area. The 4s settles into this lower energy orbital. So 4s fills first, and then 3D fills next. And then you can kind of follow the pattern from there. What fills next? 4p, then 4s, then 4d. So notice it happened again. The 4s, 4p filled. The next electron goes into the 5th energy level. And then after that one's filled, the electrons come back and fill the 4D. So this is why we talked about at the beginning of this whole idea of electronic structure. And also you talked about this in like middle school when you talked about chemistry, how every ring, every energy level is going to have this special stability that occurs when it fills with 8 electrons. Well, we're seeing that pattern here. Notice 3s, 3p fills, the next electron goes into a higher energy level, 4s. And then 3s, 3p fills, the next electron goes into a higher energy orbital, 5s. right? So the Ds are never valence electrons. You will only ever have 8 valence electrons because of the S and the P. 2 plus 6 is 8. By the time you start filling the D, you already have electrons at a higher energy level. That those D orbitals will never be valence. D orbitals will always be core orbitals. And that pattern continues all the way down this diagram. Okay, so this is an off-bot diagram. This is one way you can know the order of filling. Now, we will talk about an easier way when we get into the periodic table. And by easier, I mean you don't have to sit down and draw it. This is a pretty easy way to know the order of filling. The problem is when you want to know it, you have to sit down and draw out the chart before you can follow it, right? Well, there is an easier way using a diagram that already exists that you don't have to draw. And that diagram is the periodic table. So you can get the off-bot diagram off the periodic table. We will look at that, but we're going to go through electron configurations first before we go look at the periodic table. All right, so before we get full on into electron configurations, I just want to show you 2 more diagrams that might, you should know them because they're used as ways to show electronic structure all over the place. So I want you to be familiar with them anyway. But 2, they might help you kind of wrap your brain around this concept of an electron configuration. As we look at electron configurations, we look at, this long written out code, and it doesn't really connect with like spatially where the electrons exist very easily. You have to do that translation inside your brain. So I want to give you 2 other diagrams that kind of show you the exact same thing as an electron configuration, only in diagram form. So it connects a little bit more to our spatial reasoning side of our brain. So let's look at these 2 diagrams. All right, here's one of them. This is an energy diagram. So it shows you each orbital in terms of energy. Notice we have energy over here on the side. Low energy is going to be at the bottom. High energy is going to be at the top. This is potential energy. So remember that analogy of stacking books. Well, this is very much what we're doing with electrons. We're kind of stacking electrons inside an atom. And the more electrons we get, the more orbitals and energy levels we fill, the higher our stack is going to be and the higher potential energy we're going to have. So notice that I have each orbital here on the side. The 2p has 3 different orbitals, the x, the y, and the z. So notice that the m sub l, or that orientation piece, it is represented in this diagram. It's represented by showing 3 different boxes for the p's. D's have 5 different boxes. How many different boxes would the F's have? And if you said 7, you are right. F's should have 7 lines because there's 7 different orientations for those orbitals. Okay, so inside, as each line represents 1 orbital, inside each line, you can fit 2 electrons. Now, we tend to draw electrons as arrows pointing up for spin, one direction of spin, and then pointing down for the other direction of spin. On a diagram like this, it's really easy to get sick of writing arrows. And so instead of writing full arrows, we kind of do half arrows like that. You see the difference? It means the same thing. It's just a lazy man's way of writing arrows. So for this, we could take a specific atom like lithium that we were looking at before, and we look at the periodic table, figure out how many electrons there are, 3, and then we fill them in. We can fit 2 here. The third one has to go into the next energy level. So the electron configuration for lithium would be 1s2, 2s1. Something like oxygen. We look at the periodic table. Oxygen has 8 electrons. So again, we just fill it in order. 1, 2, 3, 4, 5, 6, 7. Okay, so before I put the 8th one in here, I want you to notice something. This is the second rule for electron configurations. It's called Hund's rule. Mrs. Searing came up with the best analogy for this that I've ever heard. It's called the smelly bus rule, right? If a whole bunch of smelly athletes get onto a bus, they don't want to smell each other. And so they're going to spread out as far as they possibly can. And they're all going to fit into one seat until they can't anymore, right? So that's what electrons do too. Electrons are going to spread out as much as they can. But they would rather pair together than move up an energy level. So I still have one electron to put in here for oxygen. Remember, I have 8. I only have 7 in here right now. The 8th electron would rather pair, which is going into this 2p orbital. It would rather do that than moving up an energy level, which would go into the 1s. So they want to spread apart, but they also want to be low energy. And so the 8th electron is going to go here into that 2p orbital. So notice they spread out as much as possible until they can't spread out anymore, and then they pair rather than going up in energy level. So for the electron configuration, we would write 1s2, 2s2, 2p, and then again, remember for the electron configurations, I'm going to group all of these 2p orbitals together. I don't have to designate the orientation that they go into. And so for this one, I have 4 that go into that 2p orbital. Another reminder, 2p can hold 6, but I don't automatically put a 6 in there because I don't have 6 electrons. I'm going to put the 4 in there because that's what I actually have. While we're on this slide, let's just talk about the third rule for electron configurations, and that is that electrons, to minimize their repulsion to each other, that's where the spin comes in. So actually one spinning one direction and the other electron spinning the other direction, that minimizes repulsion between the electrons. And so that's why one electron spins up and the other electron spins down. That's called the Pauli exclusion principle. It's called the Pauli exclusion principle, and it just is the way to minimize electrons. So the Pauli exclusion principle says if 2 electrons want to fit into an orbital, one has to spin one direction, the other one has to spin the other direction. And remember, we represent that as up and down, or plus a half and minus a half. 2 electrons that have the same spin cannot fit into one orbital together. Okay, so those are your 3 rules for electron configuration: Aufbau principle, Hund's rule, and Pauli exclusion principle. I said I wanted to show you 2 diagrams that will help us wrap our brain around this. I do want to show you that second diagram. It's called an orbital diagram. And it looks like this. It has just a whole bunch of boxes. So it's similar to the energy diagram we just saw, only instead of using lines, it uses boxes. And so each of these boxes should be labeled with, like, this first box is the 1s, second box is the 2s. Notice I have 3 boxes next. Those are my 3 2p's. And then I have a 3s, 3p's. Then notice the next one's a singular one. It's the next one that fills, which according to the Aufbau principle is the 4s. And then I have 5 boxes. Those are all the 3D boxes. And then I have the 4P boxes. And then I run out of space. You could keep going all the way up through 7F, or I guess 5F might be the highest we go. But anyway, you could just keep going. So in these, again, we put arrows. Hydrogen's going to get 1 arrow. Helium would get 2. Lithium would get 3. Notice oxygen, we just did. Oxygen is this one. 1, 2, 3, 4, 5, 6, 7. Spreads out if they can. 8. Ooh, those are kind of close together. Let me do these again. And then 8 pairs because it would rather pair than move up in energy level. Okay, so we can use this to write an electron configuration also. We look at beryllium, check the periodic table for the number of electrons it has. It has 4. We're going to put 1, 2, 3, 4 in here, and then it'll give us our electron configuration, 1s2, 2s2. Okay, so why don't you pause this video, try writing electron configurations for boron, carbon, nitrogen, and then fluorine and neon. You can use the orbital diagram if it helps you. If you don't need the orbital diagram, if you just want to use the Aufbau diagram, you are welcome to do that as well. On a test or a quiz, neither would be provided for you. You would have to draw one of them off the top of your head, and the Aufbau principle is probably easier. So pause this video, try those, and then come back and we'll do it together. Okay, so I'm going to write the electron configuration for boron. Boron has 5 electrons, so I can use the orbital diagram. 1, 2, 3, 4, 5. So 1s2, 2s2, 2p1. Carbon has 6 electrons. Let's try to draw the electron configuration without using the orbital diagram. 1s2, 2s2, 2p6, and then I run out of electrons and I have to stop. Actually, I don't run out with 2p6. I run out with 2p2. Good catch there. Okay, nitrogen is 7. The electron configuration would be 1s2, 2s2, 2p3. Fluorine has 9 electrons, so its electron configuration is going to be 1s2, 2s2, 2p5, and then I run out of electrons. Neon has 10, 1s2, 2s2, 2p6. Now, one thing to note here, notice our 2 elements in that 8th column on the periodic table. You may remember that these are called noble gas elements from previous science classes. You may remember that they're very, very stable. They don't react with anything unless they're forced to. And even then, we can't even force the smaller ones like helium and neon to bond. They're really stable by themselves. They don't like to bond. And our electron configuration gives us a clue as to why. Look at the 2 electron configurations. Can you see a similarity between them? And the similarity that you might have noticed is that they both have full energy levels. Notice helium has its first energy level is completely full. Notice that neon, its first and second energy levels are completely full. And so this gives us a clue as to why they are stable elements. There is something to do with full energy levels that causes stability in elements. This also gives us our first clue into chemical reactivity. So elements react chemically or they bond when they are not energetically stable or when they don't have full energy levels. This causes some driving force for elements to bond with each other. Okay, so I gave you a couple electron configurations. You're going to practice a couple on your own. We'll come back together and we'll do some more practice in class live. Let me know what questions you have, and I will see you in class.